Hello and welcome to week 2 of InfoViz Studio. Today we're going to be talking about visual mapping. Visual mapping happens to be one of the core components of any kind of data visualization, so let's start with there. Visual mapping, simply explained, is how you get from your data to your visualization. Let's say you have this data, 5, 6, 7, and 9, some kind of numerical series. You map that to something visual. In this case, we've chosen a line. So 5 is here, 6 is here, 7 is here, and 9 is up here. Something else is presumably mapped to the bottom axis. That's it, right? Video over. Of course, there's a lot of different things that can be mapped. And before we get to talking about what mappings work or why you should choose a particular one or how it relates to the chart types you know, we're going to have to dig into some of the details. You might have noticed that there are many kinds of visualization out there. This is from a really great resource called the DataViz Project, datavizproject.com, which captures a ton, like 100 and something or other different kinds of visualization, and gives you examples and the structure of each one. I think it does a really good job of categorizing all of these different kinds of things. Some of them you'll be familiar with, line graphs, etc. Some of them, like a radial histogram, might be something you haven't seen before. But what I want to go to in this video, incidentally, in the tutorial today, you'll go through a couple of these different types. You'll make some basic examples of it, and you'll be able to learn a little bit about what goes into a bar chart versus what goes into a line chart. That stuff is really useful, but I want to see if we can go a little bit deeper, because there's actually hundreds and hundreds of these different kinds of visualization. It's not really something that you can learn by rote. It's not really something that you want to learn, all of the different options and be able to parrot off, the best situation, the best data for that situation is to use a Sankey diagram, you're going to need to do this, this, and this. There is no rule, there's no formula. What there are is a bunch of best principles and a bunch of things that you can know. So here's an example from the Data Visualization Project. This is one of the simplest charts that we all use. It's a line graph. We all got super familiar with them last year for a bunch of reasons that will be super obvious. They show two axes of usually numerical data. Along the bottom, usually referred to as the x-axis, you have, in this case, the numbers 2 to 10, and along the left-hand side, the vertical axis, usually referred to as the y-axis, you have the numbers up to 1,000. So this shows the change over time of that data, or rather the change over the x-axis of that data, where the x-axis is usually depicted as time. But I can't really go through all of these with you. It's something that you could pick up if you worked as a visualization designer, but honestly, there's got to be a better way of thinking about this. So the first thing I want to talk about is, what do you actually have to work with when you produce a visualization? And I think it's pretty straightforward, and the easiest way to think about it is, what are the different kinds of things that I can draw? I can draw points, I can draw lines, I can draw shapes, and I can draw volumes. Everything is combinations of those or attributes of those. So speaking about attributes, there's about 5 different basic ways you can vary those shapes, those forms. You can edit size, you can edit angle or orientation, you can edit color, which can be broken down into hue, saturation, brightness, or RGB, or however you want to put it. You can edit texture of lines, of shapes, all of these different things, and obviously the shape itself. These and a couple of other smaller properties like curvature or line weight. These are all things that you might be familiar with from a visual design or information hierarchy perspective. But in a visualization context, we want to take some data and we can map it onto these things. Thinking about it in this way, in terms of components and what we can do with those components, takes us sort of down a level into the fundamentals, rather than talking about chart or diagram types. We can now think of charts as compositions of different shapes, different properties, and how they are mapped to variables. But before we get back to that, I actually want to talk a little bit about the data itself, because not all data is alike, obviously. Really, you can break data down into 4 key kinds. The first one is categorical data. Simple way to think about that is just categories of stuff that don't have any inherent order to them. A great example is students versus alumni versus staff. You can also have ordinal data, which is really another kind of categorical data, but one that does have an inherent order. So for example, child, adult, senior. Underlying those groups, which are categories, is some assumed range of ages that has a relationship within it. So the third kind of data is discrete data. This is where there is a clear number, but they are countable objects. You can't have fractions of them. I've put apples here. I have just realized now that it is quite possible to cut an apple into small pieces. I have small children. I cut apples into small pieces all the time. But assume for a second apples were fundamental and indivisible units of the universe that could not be broken into pieces. You know, people, students would have been a better example. It's much less common to cut students into pieces. And of course, continuous data, which is where it is a continuous scale. You talk about distances or talk about quantities of things where you can have fractions like liters of water or something or other. These can, if there seems like too many kinds of things, you can put them into 2 broad groups, categories, I guess. There's the category data, categorical and ordinal. Really, when you think about it, that's ordered categorical and unordered categorical. Or numerical data, numbers. We've got discrete numbers and you've got continuous numbers. And there are also some things that seem to be numbers but are actually not that numerical. Like if you ask someone to rate how much they like a product out of 5, psychologists have shown that there isn't actually a linear scale. Like a 4 out of 5 is clearly not twice as good as a 2 out of 5. A 2 out of 5 is really bad and a 4 out of 5 is quite good. You can't even assume that a 4 out of 5 means the same thing for different people, and the averages don't really make all that much sense. So if you try and average how much someone likes something out of 5 and then call that number meaningful because you've treated it like continuous data, it tends to get into a little bit of a tricky situation. I mean, get me talking one day about how teaching evaluations work. Under the hood, the university averages all of your out of 5 ratings of teaching quality, but given these 4 categories of data, given these 2 broad ideas, category data and number data, we can now return to those different kinds of visualization. And we can now start to say, all right, what kinds of data is being mapped to what kinds of property of shape? What kind of form, what kind of visual feature is being mapped to from this data? So let's have a look then at that pictorial fraction chart in the middle. That is mapping something continuous. Presumably you're comparing different percentages. So 75% of the human body is water or whatever they're depicting with that. And then maybe they would show that 11% of the body is bone. Just made that up. Seems about right though, but just made it up. Someone call me out and put the real number on Slack. You could compare those 2 amounts. That is mapping a continuous variable, percentage of your body that's made up from something, to an area. It might actually be mapping the height, but it looks like an area to us. And there you start to see where things can get a little bit messy. The person, at least that picture that they're using, has more of its area in the top part because it's wider due to the depiction of the arms. It's easy for us to get confused between things like length and area. It may be that more than 25% of that little person isn't shaded, and so people may perceive that number differently. If you need a lot of accuracy, you're going to not want to use mappings like that. So when it comes to what mapping you do want to use, it's easy to say, okay, don't use that because it'll confuse people. But what kinds of things do you want to use if you want to get people's attention? And for that, I like, at least as a starting point, to turn to cognitive psychology, perceptual psychology rather. But in perceptual psychology, has looked at these features that people perceive immediately before they even start thinking about it. They call them preattentive attributes. What they mean by that is that people perceive these things before they actually pay any attention to what they're looking for. These things, you'll have a look at them, the shape in the top one there, it just sort of jumps out at you, enclosing them in objects of a different color. This all comes back to fundamental principles of perception that we all share because we're all using a vaguely similar visual system. Color jumps out, position jumps out, the curvature of this line down here, or the density of the regions in these charts. These things bounce out at you. They almost seem to hack your attention because they stick out as a pattern. They are surprising, and they are therefore jammed into the front of your mind. That can be super useful if that's what you want to depict with your mapping. If you want to pick something in your mapping where the shape only changes when something is very, very important, and otherwise the shape is always the same, well, that's probably going to jump out. Same with line width, same with saturation. If you want to show something standing out, then using these kind of preattentive attributes can be super useful. So given what we know now about these basics, let's go back to the line chart and start to say, okay, what is being mapped here? Well, a line chart should definitely always show a continuous variable, because you wouldn't actually want to draw a line between discrete variables, like, 1 student to 2 students, because that kind of implies that it traveled through 1.1, 1.2, 1.3 while getting along the way, right? If you draw a line graph rather than a scatter plot, which is basically the same thing with the lines taken out, just the points, then you're implying a continuous transition between those things. So a line graph is intended for 2 dimensions of continuous data. Usually you're comparing something in the vertical axis that is your condition of interest, your variable of interest, and then something in the horizontal axis is the thing you're just showing it against. And then we can contrast a line graph with a stacked area chart, a stacked area graph. And these I really like for depicting how multiple things have changed over time. So this again is showing changes over time. It's showing changes in a quantity over time, and those quantities should add up to something. So if it doesn't make sense to think of all of your different components added up as being part of something, then you should definitely not use a stacked area chart. That's what you're implying by using this mapping. It is easy to perceive the overall volume rising here, but it's actually not that easy to perceive exactly how much is in the light red one, right? You can see it's getting bigger. The light red section was much smaller here. It's much bigger here. You can see the whole thing is getting substantially bigger. You can even kind of look and see the proportions. These are, at this point, it's vaguely thirds, right? But then up here, the black one has grown the most, but you can't really see the specifics anywhere near as precisely as you could by showing multiple line graphs and not stacking them. In other words, the stacking gives you a certain set of visual affordances that weren't present in the line chart, and those are a trade-off. You get some things out of your mapping and you lose others. So I know I'm throwing a lot of examples at you here, but I want to do 1 or 2 more examples from real visualizations to start to get you thinking about this idea of what variables are being mapped to what quantities. But for starters, let's have a look at a couple of more visualizations and try and think a bit about the mapping choices that they've made. This is actually a really famous example from the New York Times. They've done a ton of really quality data journalism. Data journalism is something we're going to talk about a bit more later in the course. This is a map of droughts in the US. And one thing is really wild here is that the oldest data, 1960, is down the bottom left, down over here. And then the youngest one is up here, 2012. This is an old article from well, I guess almost 10 years ago now, but you would imagine the 2020 data would be up here. And this is shown the distribution of US counties that have been declared as droughts over 60 years. So you can see that the waxing and waning. So in the 80s, you start to see this really bad drought early in the decade, then things get really wet, and then they get awful towards the end of the 1980s, really bad drought there. This is actually a technique called small multiples. They're showing a whole bunch of small visualizations aligned in some other dimension. So this has actually got a mapping within each one of these. It's a map, so maps position in space to position in the map. And then you're showing color to indicate drought versus not drought. So it's using two simple colors, one very desaturated to show no, as in we're not interested in that area, and then one very bright, very contrasty, this orange to say, yes, we are very interested in this area. They've paid special attention to making sure that if you grayscale this, they're still clearly different. They're showing a simple positional mapping within the United States, the contiguous United States, and then they're showing a simple color mapping, and then they're projecting that over time. So you can actually look through here and see how things have changed over time. I think this New York Times drought mapper was a really, really successful visualization. It showed people like, yeah, look, drought fluctuates. Drought has a strong temporal continuity. It's as in it's smooth over time. So there's more drought in years where previous years had more drought. It doesn't tend to go from everything to nothing, although it does sometimes. Look at 1977 to 1978. It's almost like it's inverted. But mostly drought changes smoothly, and drought affects a lot of the United States. You can see why this article was made in 2012, because in 2012 there was a really serious drought in almost all of the area of the United States. So another thing we can look at is interpreting one of the examples from last week. This is the Clipsal Solar Pulse app. They've used a variety of different visualization mappings to communicate different things in the different screens of the app. On the one on the left, the dark one, they're showing what is connected to what. So it's your home down the bottom, and then the different sources of energy, solar, battery, and grid at the top. And the thickness of the connection shows how much energy is flowing at the time. So they've got the Clipsal thingy in the middle, that little, it's not a pause icon, that's their little logo for their smart whatever it is. So you can see a lot of energy is coming from the solar panels, a little bit of energy is coming from the battery, and as of now, virtually no energy is coming from the grid. You can look in the third screenshot, the one with the green area chart. So here they're using area because they really want to emphasize how much money you've saved. They have a strong business incentive, and let's be honest, a strong environmental incentive as well, to show that, yeah, you've saved a ton of money, and look how it keeps going up, and it's gonna keep going up. There are points of interest, annotations along here. We'll talk a little bit more about annotations in another video. They can be super useful. There are points of interest that show all the different times when you've made changes to your setup, bought a battery, etc. And then over time, you can see even the shading is changing from light, you didn't save much money, all the way up to dark, you've saved tons of money. I'm kind of mocking this, but it's actually super helpful. It's super helpful to provide these contextual clues through shading elements and things like that, so long as by doing so, by emphasizing the emotions, the vibe, the design of the visualization, you're not getting in the way of its function. And then in this one on the right, there's a lot going on here. So you can see they've got a categorical variable, this case of where is the data from, and there's no inherent ordering, so they can use brightly divergent colors. This is the curve of what you generated, but this is the curve of what you actually used. And the coloring really shows you, okay, given what you generated, how much of that did you use yourself versus sell back to the grid. So the yellow bit shows an area where you were using less power than you were making, and the pink bit shows an area where you were using more power than you were making. The dark line is a standard line chart, so that's showing your power consumption over time. And then this lighter area superimposed on top, which gives you the shadings, lets you show the categorical variable of how much of the power of the different kinds were shown throughout. So it's got some continuous data, two series of continuous data, and then a clever little bit of coloration to break it down into the categorical variables that users are interested in. Because if you're looking looking at this, if you've got a big fancy setup with batteries and solar panels, and you want to talk about how most of the time you've made a good investment and your home is mostly self-powering, then you want to be able to look at this and say, hey, look at all that yellow area. That's where I sold power back. And hey, look, from 8 a.m. to 1 p.m., I didn't pay a cent to the utility company. So maybe the spike here where you boiled the kettle or whatever that was. But oh, look, we powered almost half of our usage through the daytime hours. That's another piece of mapping that I forgot to mention here. It's a little subtle thing in the background, but obviously solar panels work better during the day, and the white area indicates the component of the time that is day, and then the gray area shows the component of the time that is night. And obviously over the course of the day the sun gets brighter and then dimmer again, but all the user really wants to see here is during daytime, what did I use, and during nighttime, what did I use? That's where I want to leave the first lecture on mapping. In our next video, we're going to go into the kind of stuff around the purpose of a visualization. Who's your audience? What kind of context are they operating in? What kind of expertise do they have? And what kind of story do you want to use to make your point? What are you trying to communicate with this visualization? And in doing that, we're going to talk a little bit about the choices you might make when making these mappings to make that visualization effective for the purpose that is described. So, and I feel now like I have to do this every week, even though I was initially somewhat hesitant to do it. Hit that like button, subscribe with notifications on so you don't miss a video, and I'll see you in class.